All right, this session is going to be about 7.4, which is basic trig equations. Obviously, a trig equation, just an equation that incorporates a trigonometric ratio, sine, cosine, tangent, secant, cosecant, cotangent. All of our identities so far are trig equations. They are trig equations that are always true. But most of your trig equations are only true at certain values of theta or x, whatever variable you're using. So these are all examples of trigonometric equations. These are simple ones. These aren't too hard. And that's kind of what we'll start off with here initially. We'll actually start with like the simplest trig equation. It's when you just have a trig function equal to some value. Okay, so we don't have to do any preliminary algebra or anything like that to isolate the trig function. But essentially, what we're asking here is find the value of theta that when you plug it into the sine function, it's going to spit back a 1/2. Okay, and if you read through this, it says throughout one cycle of the unit circle. So that means our theta is going to fall between 0 degrees or 0 radians and 360 degrees or 2 pi radians. Okay, I'm just going to work in radians for now. So what we've got to do, there's a couple different approaches. You use the unit circle approach. Okay, so unit circle approach would be this. Essentially, you're going to move along the unit circle until you see that you are at a position where the y value is 1/2, because that's the sine. Okay, so right here we're seeing that the sine is 1/2 right there. So pi over 6 would have been the theta that generated that 1/2. So pi over 6 is one of our answers. Okay, we can keep going through, and we can get to 5 pi over 6. Okay, and we see that the y value again, sine, is 1/2. So the thetas that we use for this in an algebraic, a unit circle approach, is that theta is pi over 6 and 5 pi over 6. Okay, now you can use a graphical approach. Okay, if we remember that when we have an equation like sine of theta equals 1/2, the left-hand side is a graph, the right-hand side is a graph. So the left-hand side would be that, and the right-hand side would be that. And the solution to the equation then is it's the x value, or in this case the theta value, in which these two graphs intersect. We're seeing them intersect at pi over 6, and then again intersecting at 5 pi over 6. So that's one way of recognizing it. Another way, and we'll use this a little bit, is to use the inverse functions. Okay, now it's not as easy using the inverse functions for the mere fact that most of your calculators are not going to give you answers in terms of pi. Okay, so I'm just going to write here pi over 6 and 5 pi over 6 and see what those decimals look like. Okay. So now what I'm going to do is, if you remember the equation we had with sine of theta equals 1/2, and what we've talked about in the past, if we have sine of theta equals 1/2, we can sine inverse this side, sine inverse this side. Those are going to go away, give me theta, and I figure out what this is. Okay, so I'm going to type in sine inverse of 1/2. Remember, arc sine is the same thing, so we're going to say arc sine of 1/2. And we see then that it gives the same decimal as up here, which was pi over 6. Okay, now that's the only thing that's a problem using the calculator and the sine inverse functions on the calculator. Generally, they're going to want the pi over 6. And I would argue that most of us don't know that that is equivalent to pi over 6. Also, if you remember, the arc sine only gives answers between negative 90 degrees or negative pi over 2 and positive pi over 2. 5 pi over 6 is not in that range. Okay, so remember again. So let me just draw a picture real quick. So the sine inverse is only going to give values between negative pi over 2 and pi over 2. And the one that it gave, that should be a 2, the one that it gave us was pi over 6. We have to do a little bit of work to find that 5 pi over 6. Okay? So those are some approaches that are all going to be used intermittently throughout this. We use maybe the graphical approach a lot to check our algebraic approach. Something to think about is, that we restricted the sine function here to go between 0 and 2 pi. But we obviously know the sine function extends forever. It's periodic. Okay, so we could actually just look at this and get the thing to go on forever. And then you can see that there's actually an infinite number of solutions where the sine function in the line y equals 1/2 intersect. Okay, and for some reason it's giving that point all the way over there, way over here for some reason. I don't know why it's giving that one, but that one is then the same as that one, which is the same as that one, which is the same as that one. Okay, so the way we could get to replicate the infinite values or infinite solutions is if I look at, let's just look at this intersection point there, and let's look at that intersection point right there. Okay, they should be kind of the repeat of one another there. They are the coterminal angles. This is the first one in the interval 0 to 2 pi, and this one here is the first one beyond 2 pi. Okay, so if we look at b to c, so if I just take the x value of c and minus the x value of b, you see that their distance between one another is 6.28, which is 2 pi. So if I want to find the infinite solutions, okay, for the sine and cosine function, either one is fine. This is going to be true on each of them. You find your theta is pi over 6. If I add 2 pi to it, I'll find another answer. Well, if I add 2 pi to that, I'll get another answer. Add 2 pi to that, I'll get another answer. So what I'm going to be doing here is adding multiples of 2 pi. So usually what we do is we say we're going to add 2 pi. Now they use n or k. I like to use k. So we say pi over 6 plus 2 pi k, where k is an integer. And that will then give you all of your other solutions. So if we go back to this, if I say, so the x value of b plus 2 pi times k, comma 1/2, create a slider for k, and now I'm going to make that slider go by integers, so increments of 1. Now if I make k go to the right, we should see, so let me see this point here. Let's see where to go. Must be D that we're choosing. Okay, so there we go. So let's change that to a red X. So you can see here that when k was 0, we would have pi over 6 plus 0, which is pi over 6. So we get that point right there. And then if you go k to be 1, you can see that it then jumps to that point right there. And if k is 2, it's going to jump to that point there. K is 3 to that one. K is 4 to that one. So it looks like it's giving us a formula, and that gets those kind of coterminal solutions. Now, you see that when we do this, when k was 1, we jumped over this solution here. Well, that was the 5 pi over 6 solution. So when we go 5 pi over 6, that one is also going to be found by the infinite solutions. We take in theta, so 5 pi over 6 plus then 2 pi k, where k is an element of your integers. Okay, so this is a common practice for all functions that have a period of 2 pi. And if you remember, your functions that have a period of 2 pi are sine and cosine, secant and cosecant, but tangent and cotangent have a 1 pi period, so then this would just be pi k if it was tangent or cotangent. And we'll see a couple examples of that stuff here in a moment. Okay, so I want to do this next example here, and basically this is just kind of working one more additional step. So previously the example was sine of theta equals 1/2. Well, now I'm going to eventually get to the same thing, but we see that we started here. So what I want to do is just realize that we're trying to isolate our trig function. So that's kind of our variable thing, okay? And I'll give you another way of doing this if you prefer it. We've done it in the past in college algebra with u substitution. We can use that approach too here in a little bit. But I usually just highlight my trig function, and I try to isolate that. So I'm going to add 1 to both sides, so we get 2 sine of theta is 1. And now I'm going to try to, again, isolate my trig identity, or trig function. Excuse me. So divide both sides by 2. And I get sine of theta is 1/2. Okay? So now sine of theta is 1/2. Well, we go through that same game that we just did on the previous example, and I'll save you the heartache of going through that again. We'll just say, well, theta is pi over 6 and 5 pi over 6. And if we want to find the infinite solutions, we add 2 pi k to that, 2 pi k, and both these, remember, k is an integer. Okay, that's key. A lot of people forget that, but it's key. I can't just say k and let k be a real number, because if k was like 0.23, that's not going to generate a solution then for this equation. Another way of doing this is to, like I said, use u substitution. So we could. Now this really only works, I would say predominantly if you have just one trig expression in your equation. But I'm going to say, I'm going to let u equal sine theta. And I'm going to rewrite them. I'm going to go set, so 2u minus 1 equals 0. Then 2u would be 1, u would be 1/2. And now I'm going to back substitute. U was sine of theta, remember? So now I get sine of theta is 1/2, and now I attack it with the unit circle and answer the solution that way, or find the solution that way. And so this is huge. This is understanding when we get to this point, understanding our inverses and understanding our unit circle, and that's kind of predominantly what we spend most of our time on in chapter 6. Is so that when we get to this stage in our equations, we have that background of knowledge of what to do next to actually solve for theta. So this one here, tangent squared theta minus 3 equals 0. So I'm going to try to isolate the tangent squared. So we get tangent squared theta is equal to 3. Now I'm going to square root. So we get tangent of theta. So I introduced the square root, so it's plus or minus radical 3. Okay. So now we got to think off of our unit circle. Remember, tangent is sine divided by cosine. So I'm going to look at this point right here. I know that's pi over 6. So it's radical 3 over 2 comma 1/2. If I go sine divided by cosine, that gives me 1 over root 3. That is not the same as root 3. So that tells me then that pi over 6 is not the answer. But it automatically tells me that pi over 3 is the answer. Because remember, pi over 3 is this, 1/2 root 3 over 2. And now if I go sine over cosine, you root 3 over 2 divided by 1/2, that does give me root 3. So pi over 3, so theta here is pi over 3. It is also then, okay, this point right there, so 2 pi over 3. So remember that symmetry. Okay, so that would be where we get the positive root 3. Well, negative root 3 is going to be We think about it as negative pi over 3 if we're going to use the inverse function. But that's the 5 pi over 3 position. And we can also have that one, which is at 4 pi over 3. And that would be the situation where they're both equal to negative root 3. What is nice is these two actually are, when we talk about the infinite solutions here, they are actually duplicates. Same thing for those two. So if I start with theta equals pi over 3, and I want to add to it its period, so pi, okay, times k, again, where k is an integer. The first k, when k is 1, let's see about k equaling 1, this would be pi over 3 plus pi, which if I rewrite that, that'd be pi over 3 plus 3 pi over 3, which is common denominators, is that 4 pi over 3. Same as that answer there. So when you write infinite solutions for some of these, especially the tangent and cotangent, even though you get 4 answers here, I can actually encompass that answer inside that one if I need to. Okay. The next one would be theta is 2 pi over 3 plus pi k, where k is an integer. If k is 1, that's going to generate that one. Okay. Again, just giving you kind of a graphical representation of this. We're looking for when tangent of x was equal to square root of 3, or when it was equal to negative square root of 3. And we can see that it happens at pi over 3. Okay, when I'm looking at that one, that black line there, in this tangent pi over 3. And then again here at 4 pi over 3. And then again here at 7 pi over 3. We keep adding pi to that and getting more solutions. But then here you also see, negative pi over 3, which I mentioned previously, but we usually like to talk about it as a positive angle, so we called it 2 pi over 3. We added pi to negative pi over 3 and got 2 pi over 3. Add pi to that, and you get 5 pi over 3. Okay, so that's kind of what we're looking at there with that certain situation. And that's obviously looking at that the last version of that equation. Remember, the equation we started with was actually tangent squared x minus 3, and it was equal to 0, and we wanted to see where was that equal to 0. Well, this is tangent squared x minus 3, this weird looking graph here, but you see that it's equal to 0 at pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. So the solutions of that graph there, just like any other equation we've ever worked in the past, the equations to that, the solutions to that are encompassed in the solutions. Oh, I don't know what I'm doing there. To this tangent of x, and then square root of 3, and y equals a, and y equals opposite a. So the solutions to this are inside the solutions to this, or are the same as the solutions to this. Okay, it just makes it a lot easier for us to take something like this green curve, do some algebra to it, to break it down to our parent functions and analyze our parent functions that way. All right, so let's go to the next one. It says solve the equation 2 cosine squared theta minus cosine theta plus 3. Okay. First thing I want you guys to notice here is that there's a certain structure to this. It's a cosine squared, a cosine to the first, so if we kind of analyze this algebraically, this is quadratic form. think about it this way. If I let, and we can solve it this way. There's nothing wrong with doing it this way. But if I let cosine theta equal u, this thing would be 2u squared minus 7u plus 3 equals 0. So I think that's the way I'm going to approach this. I'm going to leave it this way, and then I got 2 times 3. I'm using the AC method, so it gives me 6. So we'll look at -1 and -6. So I'm going to go 2u minus 6, or sorry, 2u squared minus 6u minus 1u plus 3 equals 0. Group the first 2, the back 2. So I'll get a 2u coming out of the first 2, would be u minus 3. Get a -1 coming out the back 2, so u minus 3 again. So I get 2u minus 1 as a factor, and u minus 3 as a factor. So that gives me 2u minus 1 equals 0, u minus 3 equals 0. So then 2u is a half, or sorry, 2u is 1, u is then a half, and then here u is 3. Okay. Remember what what u was. U was cosine theta. So we got our cosine theta back substituted is equal to 1/2. Here I get cosine theta back substituted gives me 3. And now we just have to answer those. Okay, so this is what we've been working on in chapter 6. If I had those two things, when is cosine equal to a half? Cosine is equal to a half. On the unit circle, cosine is equal to a half at theta equaling pi over 6. Okay, and remember, so that'd be about right there on my unit circle, but it is also right there. Okay, that would be the next place that we have, or not pi over 6, I'm sorry, it's pi over 3. My apologies. So pi over 3, and this would be the next place, which is going to be 5 pi over 3. And this one, this 5 pi over 3 one, remember we can't get that from our calculator. We can get pi over 3, now give me a decimal version of it, but I can get pi over 3 from taking cosine inverse of 1/2. It will give me the decimal version of pi over 3. Calculator will not give me that there, because the cosine inverse, if you remember, is only defined for that interval. Okay, and we're obviously this point here is outside that. Now the next one is the question. Okay, well when is cosine of theta equal to 3? So for what theta value, what angle measurement can I plug in that the x value on the unit circle gives me a 3 back? Well, remember, we're in the unit circle here, so the x values are only between -1 and +1. There's no way it can give me a 3 back. Okay, so that is undefined. There are no solutions from that. Okay, remember, if we're looking at a graph of this, okay, we can see when does cosine of x equal 1/2. All right, so we're seeing that again, pi over 3, and then there at 5 pi over 3. So we're seeing those solutions. Okay, but now the question is, well, what if that 1/2, like in the second part, was a 3? When does the cosine intersect this line up here at 3? Well, it doesn't. It only goes from 1 to -1, and it oscillates between those. So there's no solutions. There's no solutions from this second part, and that happens from time to time. Sometimes you'll get 2 solutions from that one, and you'll get 2 solutions from that one. If it's usually something squared, like maybe tangent or something like that, you might actually get 4 solutions from that one and 4 solutions from that one, just because of the plus or minus aspect of things. Now you can, so using the U substitution approach is good, okay, but some people don't like using that or don't need to use that. So we have this, and they're able to justify to themselves, okay, well, cosine is the variable part. So they're going to say, well, this is then 2 cosine squared theta minus 6 cosine theta, and then we'll have the minus 1 cosine theta, and then plus the 3 equals 0. So all I did was I grouped this at the same time that I kind of used the AC method. But now they look at this and say, oh, I can take out a 2 cosine theta out of the first two terms, and it leaves me cosine theta minus 3. And here they say, well, I can't take out anything but a negative 1. So it leaves me cosine theta minus 3. And then b2 cosine theta minus 1 and cosine theta minus 3 equals 0. And then they get 2 cosine theta minus 1 equals 0. Cosine theta minus 3 equals 0. So this eventually gives me cosine theta equals a half. And this will give me cosine theta equals 3. It's total personal preference. I think this kind of gets messy sometimes, leaving the cosines in there. There may be questions where it's unavoidable and you can't use U substitution. But if U substitution is available, I'm going to do that because I think it just makes things cleaner looking. It's less writing. I never write cosine out every single time. So those are just kind of my personal preferences. I'm going to use U substitution when it's possible. Okay. So the next one here says solve the equation 5 sine theta cosine theta plus 4 cosine theta equals 0. Okay, so this one, and I'm just going to rewrite it over here so we have a little bit more room. 5 sine theta cosine theta plus 4 cosine theta equals 0. When we work with equations in general, obviously if it's a linear equation, we don't have to do this, but if it's anything other than a linear equation, a lot of times the number one thing to think about is there a GCF? And then after we check a GCF, we go through other factoring techniques. If I look at these two terms, there is absolutely a GCF here. I can take out a cosine theta out of both of these. It makes me 5 sine theta plus 4 equals 0. And now I've got two numbers being multiplied together, and they give me 0. So I can use the zero product property. When is cosine theta equal to 0? And I've got 5 sine of theta plus 4 is equal to 0. Well, I can go sine of theta equals, this will be negative 4/5 eventually. I think you guys can do that algebra. Subtract 4 and then divide both sides by 5. And then we got to ask you, okay, when is cosine theta equal to 0? Well, unit circle says cosine theta is equal to 0 right there. That's when the x value is 0. That's at 0 radians. So theta is equal to 0 radians. It also comes back to 2 pi. 2 pi is also going to give me 0 as a result here. Okay, I'm going to highlight that because I want to talk about it here in a little bit. So I remind myself. Now I get to this, and I think, okay, well, negative 4/5. Negative 4/5. I don't recall anything off the unit circle of negative 4/5. So in this situation, this is where we have to grab our calculator. Okay. So if you're not going to get, so obviously key numbers off the unit circle are like 1/2, radical 3/2. If it's tangent, radical 3, radical 3 over 3. If it's secant, cosecant, 2. Maybe some undefineds might exist at certain times. But those are the values usually that are going to allow us to, from memory, use our unit circle. Negative 4/5 is not a value off the unit circle that we're accustomed to. So we have to even use our calculator. So I'm going to take, and I want to do this in radians. Okay, so I'm going to take, what's it, sine. Okay, so I'm going to take sine inverse of negative 4/5. Okay, so it gives me that amount there. Okay, what that means to us, let's draw a picture here real quick. Is that the sine inverse is giving me back now an answer of negative 0.927 radians. Well, this is negative 1.57 radians. This is positive 1.57 radians. It's terrible. 5. Okay, so it's giving me back like something maybe like right there. Okay, now generally speaking, we want answers between 0 and 2 pi, and we'll talk about that here in a moment. So that answer I don't really like. I'm going to rewrite this, and this is what WebAssign is going to want from us. If that's negative 0.927, okay, I'm going to add 2 pi to it. So arc sine of negative 4/5, and I'll add 2 pi to it, and that is actually the radian that we prefer, 5.355. Okay. Now, just think about this. This was, so the y value here, that y value right there would be the negative 4/5 or negative 0.8. Well, doesn't that exist over here as well? There's an angle right there that would be still generating negative 0.8 back. So what I'm going to do is try to figure that one out. Okay. Now, a couple different ways you can do this. My initial thought is to use the fact that we've got symmetry here. So this angle here was, if we think about the absolute value, it's 0.927 radians. So this angle here is 0.927 radians as well. That angle right there. Well, that's pi. If I go all the way around to there, that'd be pi. And then to get to there, I would need to add that 0.927. So I'm going to take and type in, so arc sine of negative 4/5. I want to get the positive version of that. So I'm going to negate it. So now that would give me this right here. And then I'm going to add pi to that. And it gives me that measurement. Okay? So I'm going to write those two numbers down over here. So we got theta from this information right there. We get theta to be that 5.355. 5.355. And we also get theta to be 4.0688. 4.0688. Okay? And the only thing I want to make sure that we understand here is I should be able to check this. Okay? So, looking at this set of solutions, let's go back to Desmos. Okay, so let's just call this value here T. It doesn't matter what letters I use here, T, and let's call this value here I don't know, M. All right, so now if I just ask it, okay, well, what is sine of T? You see that it gives me back my negative 4/5. If I ask for sine of M, it gives me back again my negative 4/5. So I know that those are the correct solutions, okay? Now the only thing that we have to be aware of is that when we're solving for theta, and usually the directions will say this, I don't think my directions for this example said it, okay? They will tell you a certain domain that they want you to find answers for, okay? So they might say for theta to be between 0 and 2 pi, like that. Or they might say 0 to 2 pi, like that. Notice I used a parenthesis here and a less than sign there. And the reason I'm doing that is, and this is usually what WebAssign will do, and a lot of textbooks do, is that answer right there is redundant to that one. Okay? Because if I want to find like the infinite solutions, I would take theta of 0 and I would add 2 pi k to it, where k is an integer, and we see that formula, when k is 1, gives me that right there. Okay, so a lot of times that one will be a redundant solution, and they don't want you to type that in for some reason. So my thought is, when you're working on WebAssign and you're doing this, you could get that answer, that one, and that one. You did everything absolutely 100% correct. You go to type it in, and it says, nope, you're wrong. And you might not be seeing why you're wrong. Look at the interval that they're asking you for, okay? Now, if they say on an interval of all real numbers, or they don't tell you, or maybe they ask you for the infinite solutions, then you would say theta equals 0 plus 2 pi k, okay? Or obviously you can just write that as 2 pi k. And then this one here would be, obviously I'll add 2 pi k to that one, and I'll add 2 pi k to that one. Again, all of these were k as an integer. These tend to be things that throw people for a loop because, again, they're not numbers that we're accustomed to off the unit circle, but they are there on the unit circle. We just have to use our technology to generate them, okay? Now, if you're doing this in degrees, maybe it's a little bit easier in degrees. Think about doing this in degrees. If I go cosine inverse, or sorry, arc sine, so sine inverse of negative 4/5, it gives me negative 53 degrees. And it might be easier for you to figure out, okay, well, negative 53 degrees as a positive angle, okay, is going to be that 306, okay, which that 306 in radians is that 5.355 number. And if you want to, make sure that that's true, we can do this. I can take that A, I can make the 306 an A value and say, okay, A times pi over 180, you see that it does transform to that 5.355 number, okay? Then, obviously, down here, we would see that this, obviously, this here, let's get rid of that real quick. This would be the 56 degrees. Then if I add my pi to that, it's going to give me yes, what am I looking for? I'm actually looking for, so trying to find this second angle. Did I saw the picture? This second angle here, remember this was negative 50, was it 53 degrees? So let me see here, arc sine negative 4/5. So negative 53 degrees. So if I make that positive 53 degrees, so positive 53 degrees, but now instead of adding pi, I'm going to add 180, and there's the 233. So from here up to there would be 233 degrees. And now we can see that if I go, let's just call this t again. If I go sine of t, you're seeing then negative 4/5 coming back. And if I go sine of a, you're seeing negative 4/5 again. So you can do it in degrees. Initially, I think degrees are easier. But a lot of your web assignment stuff is not going to ask for your solutions in degrees. They're going to ask for them in radians. So I wanted to see an example like that. All right, so example 4 is just kind of reiterating what we just talked about, just kind of skipping over all the preliminary algebra to isolate your trig ratio. Right now it's saying sine of theta is equal to negative 0.3. Well, if I want to find theta, now this is a number that is not, we're not accustomed to on the unit circle. It is on the unit circle, so remember negative 1 would be down here, so negative like 0.3 would be there. So if I'm looking at my unit circle, I'm looking for, basically those two positions. Okay, so I'd be looking for that angle there, and ultimately then that green angle as well. So using my calculator, we can do this. We're going to take the sine inverse of negative 0.3. So it's exactly what we just did. We have to use our calculator. So I'm going to arc sine of negative 0.3. It gives me negative 17 degrees. Again, remember, we don't like negative angles. So I'm going to add 360 to that. And 342 degrees, 0.54, is going to be talking about that point right there. Okay, that's that terminal point. If I go arc sine of negative 0.3, I'm trying then to get this position over here. Well, if you remember, same picture as before, this red angle there and that red angle should be the same. So I'm going to use that symmetry to help out. So that red angle right here where my cursor is ultimately 17 degrees. So I'll just put a negative out here in front to make it a positive 17 here. So I've now captured on my calculator this angle where my cursor is. Well, to find out the blue angle, this would be 180 plus then that 17. So I'm going to add 180 to this. And those are the two angle measurements then that I'm looking for. So I'm just going to call this one A, and I'll call this one B. I'm just going to run through a check here real quick. If I say sine of A, you see that it gives me negative 0.3. So plugging in that angle to the sine function gives me negative 0.3. If I say sine of B, same thing. Okay. Now if I was doing this in radians, okay, now obviously this stuff here in radians, that needs to become a 2 pi. And this becomes a pi. And we get the same thing. So that was the, I don't remember what the angle was in degrees, but that would give me that first angle we're talking about. And this is the, I think this was like 197 or something in degrees. Okay. So you have to be able to bounce back and forth between those types of solutions, radians or degrees. Like you said, for the most part, they ask for radians. So this would be what they're looking for. Now, when they ask you to type in like the infinite solutions, they'll tell you how to round these. They'll tell you, like, round to 2 decimal places, 3 decimal places, whatever. But then because it was a sine, so this one, the infinite solutions for this one would be plus 2 pi k. And this one here would be plus 2 pi k. Okay, so this next example, again, this one is going to be quadratic in nature. We've got something squared, something to the first power, and then our c term. So we're looking at letting u equal sine of theta. So then we would have, when we substitute here, we have 5u squared minus 21u plus 4 equals 0. AC method is going to give me so the AC method is going to obviously give me 20, so we're looking then at negative 20 and negative 1. So we go 5u squared minus 20u minus 1u plus 4 equals 0. Group the first two, group the back two, 5u, u minus 4, negative 1 comes out, u minus 4, and then we have 5u minus 1 equals 0, u minus 4 equals 0. So this will give me u equals 1/5, and this will give me u equals 4. Now remember what u was. U was sine. So back substituting will actually give me sine of theta is equal to 1/5, and sine of theta is equal to 4. Now the easy one is this, because the sine is never going to be outside of negative 1 to 1. So that's not going to give me any solutions. Now sine of 1/5, it's a positive 1/5, so I know I should have answers that are coming from the first quadrant and the second quadrant. Okay. Now 1/5 is not something that we know off the unit circle, just like the last couple examples we did. So we're going to take our arc sine of 1/5, and we get that. Now that should be in radians right now. Let's go back to degrees. It might make a little bit more sense. So 11.5 degrees. Okay. Well, if you remember then, if I'm 11.5 degrees, then that is obviously like that angle right there, 11.5. Okay. So then the angle over here, because of the symmetry, that's still going to be 1/5 for the y value. That's 11.5. So how do we get that actual angle? So remember, theta always starts from standard position. So this is one of our answers, 11.5. And the other one, to get this red angle, we're going to take 180 minus that 11.5. And it gives me that number there. Okay. So then we should be able to check this. We should be able to check those two answers. We're looking at, so is the sine. So I'm going to say the sine, let's call this value A. We'll call this one B. So then when I get sine of A, it gives me 0.2 or 1/5. Sine of B also gives me 0.2. Those are the only two numbers that will do that for us. If we're in radians, then nothing really changes. Okay, other than, so instead of taking 180 minus the arcsine of 1/5, it would be pi minus the arcsine of 1/5. So we'd have 0.2 radians and 2.94 radians. So if we're looking to write the infinite results or infinite solutions to these, it'd be theta is 0.203, whatever you want to round this to, or 213, say 6 here, plus then, since it's the sine function, it'll be 2 pi k, and this one would be 2.94 plus 2 pi k. So that's if we were doing it in radians and we wanted the infinite solutions. Going back to degrees, if we want to do this in degrees, same concept. Remember, this would be 180. Actually, how did I have that? So it would be, 180. So it'd be those. So it'd be 11.5. 3 degrees plus then 360 times k. And this one would be 168.463 degrees plus 360 k. And obviously here, k again has to be an integer. Alright, so we'll do the next example here. Find all solutions to cosine squared minus cosine minus 30. So again, another quadratic. I'm going to let u equal cosine theta. So then we'll have u squared minus u minus 30. At that stage, then what is it? U minus 6, u plus 5. So it'll be u minus 6 equals 0, u plus 5 equals 0. So then we're looking at u equaling 6 and u equaling -5. So I'm going to go cosine, right? Back substitute cosine theta equals 6, cosine theta equaling -5. Well, remember, cosine only goes between -1 and 1, okay, for your essentially your x values, and that means it can't get to 6 and it can't get to -5. So this equation has no solution. So let's kind of look at that graphically real quick. If we go cosine squared x minus cosine x plus 30. I guess it was it plus 30 minus 30, I think. Minus 30. and we graph it, and there we go. And then obviously that does not cross the x-axis, doesn't cross the y value equaling 0, so there's no solution here. What's interesting about this is it kind of looks like if you've ever like done like if you've got an Apple Watch and you take your heart rhythm, okay, this kind of looks like that, okay, and you can start to see then that those things that we've used in technology, EKGs, EEGs, a lot of that data can be written or interpreted using sine and cosine equations. Let's go down to the next one. All right, so this example is like example number 3, where we had a like term, okay, a GCF. If we look at both these, they have a tangent, and so I'll take that tangent out. So I'll have tangent of theta. That's going to leave me then 5 sine of theta minus 4 is equal to 0. Okay, at this stage then you've got a product of two things equaling 0, so then that means that tangent of theta is equal to 0, and that 5 sine of theta minus 4 is equal to 0. So sine of theta is equal to 4/5. That being said then, we're going to have to evaluate, okay, where is tangent equal to 0? Well, remember, off the unit circle, that tangent is sine divided by cosine. So if I go -1, 0, or I guess that's positive 1, this is -1, 0, 0, 1, and 0, -1, the places that I get 0 would be where I take y divided by x, and I'm able to do that. Okay, so if I did take that y divided by that x, that gives me 0. Over here it gives me 0, and remember up here, y divided by x would be undefined, and down here would be undefined. So my two positions that give me values for theta here would be 0 radians, or 0 degrees, and pi radians, or 180 degrees. Over here, again, 4/5, not something that we're accustomed to. We've already done one, I think it was -4/5. But what we're going to do to find theta here is we actually have to take the sine inverse of 4/5. And remember, the sine inverse is only going to give you something out of those two. But 4/5 would be about there. If that's 1, that'd be about 0.8. So there should be a point right there. There should be an angle right there, theta, that the y value is 0.8. But there's also going to be a theta right there that is also going to give me a y value of 0.8. So the calculator gives the first one. So when we go, and we'll do this I'll do it in degrees first, and then we'll just transition into radians after that. So we're going to go arc sine of 4/5. Okay, so the calculator gives that first 53 degrees. Okay, so that 53 degrees is that angle right there. Okay, now we then need that angle. Okay, well, what's nice about this is that this purple angle should be the same as this dark green one, which was 53. So then find the light green one from standard position all the way up to this terminal ray right here. We're going to take 180 minus that 53 degrees. So 180 minus the arc sine of 4/5. And it gives me 126. So those are the two angles that we're looking for from this 4/5. Just quickly, if I go sine of, again, calling this A, And this is just a check. You've been seeing me do this a couple times now. And it's really beneficial. Obviously, I know that first one's going to work because that's the calculator gave me that directly. I like to do the check, especially with the second one, to make sure that when I put B in there, I do get 0.8. And when I put A in there, my keyboard stopped working. Give me a second. Okay, when I put A in there, I also get the 0.8. If I were to do this in radians, then obviously the only thing that changes is that this 180 is not 180 anymore, it's pi. And I have 0.92 radians and 2.21 radians. Radians are hard to kind of wrap your head around with these types of questions. But if you can remember that we've got 0, this is obviously pi over 2, pi, 3 pi over 2, and then 2 pi. If we can remember, this is about 1.57. This is obviously 3.14, and this is 4.71. If we can remember those approximations for those quadrantal angle measurements, then it is a little bit easier to kind of justify and realize what radian measurements, if they make sense to us when our calculator computes them for us. Again, if we then needed to come up with the infinite solutions here for theta would be obviously 0 plus, now it's because we use tangent in this one, it'd be plus pi k. Okay, now I could write another one that says theta equals pi plus pi k. But think about what happens here. If I go k equaling 1, that gives me pi here. Well, how do I get pi down here? Well, if I let k be 0, that would go away and leave me just pi there. So these, there's nothing wrong with having both these on your test. If you were asked for infinite equations and you wrote both those, they are fine. Okay, but what I want you to see, and I'll show you here in GeoGebra, is that they are redundant. Okay, depending on what your k value is, and this one's going to lag behind by 1. But if this one lags behind 1, so when this is a k value of 2, I'll get the same answer as if this one was a k value of 1. Over here with the sign of 4/5, again, the theta was, I think it was like a 0.9 something. 0.927. So then we're going to say plus 2 pi k. And the other theta was 2.21 plus 2 pi k. And that would be your series of infinite solutions. Now, if we want to look at this, we should be able to recognize this through GeoGebra. Okay, so let's just type in the original. Let's go 5 tangent of x sine of x minus 4 times tangent of x. And what we'd be interested in is where this thing is equal to 0, so we're looking at x-intercepts. So let's actually put y equals 0 in here, and you can see then that what we end up with is, let's put a point on here. Okay, so it puts that first point there at A. And I'm going to then take that point A, so I'll take the x value of A and add to it pi times k, and then comma that with 0. So this is an ordered pair. The way this is written, taking the x value of that coordinate, add pi k to it, and then pair that with a y-coordinate of 0. So this pairing with the y-coordinate of 0 is just going to make sure that the next point that's plotted is still on the x-axis here. So I do that. I'll create a slider for k. And you see then when k is an integer, it's giving me those intercepts. Okay. Now, so that would be the information for that tangent portion of this last part of the equation, the process. If we were to type in, let's go find this intersection point right here. So C. So I'm going to take the x value of C, add to it pi times, instead of using k, I'll use n now, comma 0. So we can make another slider for n. And again, I'm going to make sure that that is going by integers. And what I just want to do is demonstrate here that, you know, how you can see these points. So B is moving and D is moving. So B and D. Let's make those. So let's make B red. Make it pretty big. We'll make D blue, and we'll make it an X. All right. So you can see that when we use like n to be 0, we can get that point right there. But that's the same thing as if k was at 1. So that's the idea right here that I was explaining, where these two formulas, these two ways of writing our infinite solutions actually follow, they're one behind each other. So if k is 2, then n's got to be 1 for them to be the same. But they are a rule that is redundant. Okay, so you don't necessarily need both of them. Now what I don't have here, and we see that we're skipping over like that one right there, it's not 2 pi over 3, but let's see if I can kind of create this. So it would be, so the x value would be the arc sine of 4/5, comma 0 would be the y value. So it gives me that point E. And now if I take the x value of E and add to it 2 pi, let's just use k, comma 0, it should then give me, you can kind of see that, let's hide B real quick, hide D, hide C. So right now when k is 0, obviously E and F are on top of each other. They're the same point. But when k is 1 now, we see that we jump over to that. Okay. When k is 2, we jump over to that. Okay, so that's nice. Now we're also missing, so that was this point there that we were trying to replicate. We need to also find this one. So if I take and find, let's see here, that intersection point, not that one. Let's see if we can get this. Intersect that and that. Well, for some reason it's not letting me kind of grab that point, but let's go. So it would be, we can do it this way. Really, arc sine of 4/5. And then remember what we did with that, and go back to Desmos here. What we did with that was we subtracted that from pi. So that's what I'm going to do here. So I'll go Control Z through the arc. I'll go pi minus arc sine of 4/5, and comma 0. And you see that gives me point J. And now if I take j, then add 2 pi to it times k. And now you can see as I run through k, those points f, so E and J correspond to F and K respectively. And then to those F and Ks, and you can keep doing that progressively throughout the entire thing. So that's hopefully a good explanation for how we deal with these initial trigonometric equations. Kind of giving you a little bit of foreshadowing where this is going to go in the next couple sections. Here, these equations have, it's still quadratic.
These are fun.
It's still quadratic, but now you have a cosine and a sine, so that's a problem. So then we'll have to use an identity to adjust for that. Same thing here, cosine and a sine, so we have to use identities to adjust for that. These equations here, now instead of a theta or an x, we'll have 3 theta, 2 theta, 2x, 3x, so we'll be talking about what we call our multiple angles. And there's a separate process for that. Here you get a half angle. So that's kind of where some of this stuff's going to lead. And hopefully we can see enough examples to assist in any issues that you might have. The one thing that I want to make sure that you guys understand, and there's a lot of videos on my website that discuss this, is that how do we find these extra angles? Okay, when we use the arc sine, the arc cosine, the arc tangent, they give us the initial angle. But remember, because of the symmetries of the unit circle, there's going to be another one out there that we have to be able to capture. We have to understand that last process in these equations to be able to do that, or you're going to miss half of your answers. Again, remember, if you have questions on anything, screenshot that, send it to me, show me your work. I can get back to you as soon as possible with a description. If it calls for a video, I'll make a video. If it doesn't call for a video, I'll just write on top of your picture. Still using my website. Okay, under section 7.4 on my website, there's going to be more and more examples. Other people, other teachers, some of me, previous courses, maybe even some of the homework questions that you're currently working on website are already explained in there. So use those resources, okay? Just the videos that I make here are to introduce things, but you still have all those resources that we've been talking about using throughout the rest of the course.